Hey everyone. So today I want to take a look at how to define a fiber element in OpenSees. We're going to do so looking at this example that I've kind of envisioned. We're going to take a look at this concrete section, make a fiber section out of it, and then we're going to create a simple cantilever model over here that uses the fiber section in some nonlinear beam columns. I'm also going to spend a little bit of time going into the theory behind what fiber sections are, some of the key assumptions. We'll talk a little bit about how OpenSees handles local coordinate systems. And then in an accompanying video, I will go a little bit deeper into the two main types of nonlinear fiber elements in OpenSees, which are the force-based beam column element and the displacement-based beam column element. So let's take a look at the model that we're going to define, and then a little bit of theory behind beam column elements. So we will define this cantilever in terms of 4 nodes, and between each of these nodes is going to be a fiber beam column element. Fiber beam column elements are a distributed plasticity nonlinear element. So what this means is, in theory, nonlinearity can occur at any point along the element instead of just the ends. So in a lumped plasticity element, you could only have nonlinear at the ends. And the way that this works is along this element. So if we think of this as our element going from node 1 to node 2, there's going to be a number of integration points. Each integration point has some section that we've defined. And when we go to figure out the response across this section, like say the force, we do so by integrating across the fiber section. So the fiber section itself will be just like we make this section into a number of discrete areas called fibers. So if you think of the whole concrete section, we'd split this up into a number of fibers, like all the way down. And we also do the same thing for the steel. Each fiber section has its location from the centroid, and as well an area and a material property. A big assumption that this that all fiber sections make is that the strain distribution across the section remains linear, or another way of saying that is plane sections remain plane, if you remember a little bit of Euler beam theory. So if we think of the strain distribution, it might look something like this. The top and bottom don't have to have the same strain amount, but it does have to be a linear distribution. And this strain will have two components. It will have a normal component, so theta naught, and that's just so there will be some sort of constant strain across the section, and it will have a curvature component. So we'll multiply y. So let's just define y. So if y is like upwards in the local beam coordinate, the strain as a function of rotation will be curvature will be y times the curvature of the section. And so in this case, the top and the bottom values are equal. So we can write epsilon equals epsilon naught plus, oh my goodness, plus y times phi. Pretty sure this is phi. I don't actually remember if this is phi. I'm pretty sure this is phi in Greek. And then, of course, if we want to figure out when we want to figure out the response across the section, it's just a matter of summing up the contributions of each individual section. So We know the strain because we know the nonlinear material properties. If this is like, say, concrete, this is stress, this is strain. If we know the strain at, say, like this fiber from over here, we can figure out the stress. And then, of course, the normal force will just be the summation of all of the stresses in every fiber section multiplied by their respective areas. So in a nutshell, that's what's going on very roughly in each individual fiber section. I think now let's take a look at the local coordinate system in OpenSees. And just to be clear, this edge right here is this edge right here in the model, if that's not clear. So a typical, like if we look at the global coordinate system, it will be defined in 2D like this. So x will be going to the right, y will be positive, well, up, positive upwards, or just upwards. And the way that local coordinate is defined for elements, so if we say define an element like this, the local x prime, will be in the direction between the two elements. So if we define 1 and 2, so we're going from 1 to 2, x prime will be in this direction if x prime is the local coordinate, the local x-axis. And then going out of the plane, in 2D, z is always going to be out of the page, so we can think of this as z prime, and then y will be perpendicular to x and z, and specifically using the right-hand rule. So if you put very technical, I know, your pointer finger in terms of x prime, your thumb in terms of z, then y will be your middle finger. So this is how these axes are defined. So if we look at that over here, this corresponds to y prime looking like this, and z prime looking like this. I just wanted to get that out of the way because we're going to be defining now we're going to be doing, we're going to figure out what's going on with this beam. We're going to actually put in like the XY coordinates for each of them. And it'll be confusing if we don't have our reference set up. So now we have enough theory to start actually defining our model. So let's go and get into that. I will start by showing you the directory structure that we're going to be working with. So this is a blank directory where all our files are going to be, files. I'll create a folder called documentation. And I'm creating this because we're going to be doing a little bit of pre-processing that's not in Python, as sacrilegious as that is. And then we'll create a file. I'll call it main analysis. And we will make it a Python file. So the main analysis file is where we'll be calling all of the functions that we create and running our analysis. And I will create another file called ModelFunctions. So this ModelFunctions file is where we actually create the functions that will define our sections and materials, and then ultimately define our model. Getting into our analysis, the first step is actually going to be to create an Excel sheet. And what we're going to do is we're going to get the information from this concrete section, and we're going to save it here. So we'll just say concrete section, open it up. Oh my goodness. No, stick. And I'll just get a quick snip of this. Okay. So the reason why I like doing this in Excel is because it's really convenient to have like the visual information and then like the geometric information stored in the same place. So when we think about what we need to do to define the section, we actually need to have like the Z, Y coordinate for each of the rebars in the model. It's a little bit easier to do the concrete because it's just one rectangle, so we can define it all at once. But for the rebar sections, we are going to need the actual coordinates. So let's get those. Say Y coordinates. Recall that Y is upwards in the local axis and Z is X, or side to side in the local axis. So we'll say X coords. And then we will just get each of these values defined from the centroid, in distance from the centroid. So we'll start by getting the absolute values. Let's say going from the bottom to the top, 7, 150, and then 75 down from the top is 250, 450. Doing math is hard, guys. And then we will get the Y coordinates similarly. So 50, I'm saying this one's in the center, so, and then 350. And then I'm just going to subtract the centroid value from each of these values. So 300 to the center, the y-axis, and then also 200 because that's in the center of the z-axis. Okay. So now we just have this saved. The information is there. It's pretty convenient if we ever want to access it. It's nicer to have it saved like this as opposed to just in like some text file somewhere. You can actually see what's going on. So that's the way I do it. Now let's start coding. IDE ready. And let us, what do we need to pull up? I'm just going to make sure we have model section files open. So that's where we'll start. And the very first step is I am going to sketch an outline of what this looks like. So if you recall, we want to define this as our model. So we're going to need to have some elements, and we're going to define our section. The section will have some materials. We'll use some pretty basic nonlinear materials for those. But it's mainly going to, like, the code will occur in 2 blocks. We'll have a GetSections function, lowercase g, GetSections. I include this pass so we don't have a little error up here. We'll get rid of the pass eventually. And then BuildModel. So we'll have the bulk of our model will be created by these 2 functions. And we also need to import. So I will import. We'll need OpenSees and NumPy. And I'm also going to define the units. I think I'm going to fast forward here because don't really need to see me do all that stuff. So. Okay, so here are our units. we're gonna need meters and pascals because we're defining stress. So I'll now get into the sections function. Let's start by doing a quick sketch of what this function will look like, similar to how we've sketched out the program. So to get the sections, we'll need to first get the material properties. Get materials. And then we need to do a little bit of pre-processing for the geometry. So geometry. And should be lowercase. And then we'll actually need to define the sections. And I'm saying sections. I'm also, in addition to, so if we go over here, we will define a nonlinear section using all these materials, but we should also define a test section just to make sure everything's working. So we'll define the test section, and we'll define the actual section. And then we will also need to define just information about the integration points and the beam column, the transformation, that's what it's called. So you'll use a linear or like p delta transformation, and we'll need to define that. So okay, perfect. Let's start with the materials. And whenever I create models, I like to have a few standard materials in there. So first one will be steel. So this is just an elastic steel property. I like to have a flexible material, so you flex. So this has a really low elastic modulus and a rigid material. And this will have a really high elastic modulus. And so we will create the uniaxial materials now. So uniaxial material, I have this one memorized. So sorry, we'll create elastic materials for each of these. And elastic material is pretty simple. It's just elastic, your tag. So we'll call steel 1. And then let's just copy paste this guy 3 times. We'll put in flexible, and I like to have flexible as 10 and uniaxial as 20, or excuse me, and rigid as 20. Okay, and just so that we can keep our sanity here, I'm going to actually create a call of the function down here, and we'll continually run as we're building up this function, as opposed to just coding it all and then checking at the end if it works. As we go through making the function, we'll continuously check if it works as we define various sections. And of course, we'll need to have a wipe command, or else everything will explode. So let's go. What's going on here? That took a suspiciously long amount of time. Alright. Guess my computer just had a slow fit. Okay, let us define the rest of the materials. So the next 2 materials are a little more complicated. So we'll pull up the Wikipedia. And what I'm going to do is I'm not going to spend a lot of time on the actual material properties for these materials. I'll go through them with you. This isn't really intended to show you how you can model these in like the most accurate way. Really, I'm just trying to show you how to define the fiber section. So please don't please don't use my numbers and assuming that they're reasonable for an actual beam. So yeah, with that caveat, we're going to use a steel O2 material. This is a pretty standard material for steel. I'll show you what it looks like, and we'll use a concrete O2 material. So steel O2, basically this material has an elastic modulus. It has a yield point and a post yield point. So that's these three parameters. Everything else, these transition parameters, influence how it changes from the first slope to the second slope. And then all these parameters are like really only important for cyclic loading over here. And then concrete O2, this is a basic parabolic concrete model. I think they call it, oh geez, it's like Scott Kent. Does it say here? Crap. But there's a there's a name for the basic parabolic model which escapes me at the moment. And this is a implementation of that. So I have a set of parameters prepared already, and I'll copy paste them in so we can be judicious with our time. But before I do that, let's actually get the commands in our model. So we'll get the steel one. So define the steel, and I'll copy paste this twice. Once, excuse me, copy paste it twice. So we will have the reference of the material and the arguments if we ever need to come back to it later. We don't need any of these optional parameters. And the values I'm going to use, yield is equal to 350 megapascals, pretty standard. E naught equals 200 GPa, and B equals 0.02. That's, again, for steel, these are all pretty standard material properties. What's it mad at? Oh, and I will call this material 2. Okay, that's our steel material. And where was it? Haha, okay. Now let's define the concrete material. So I'll do the same sort of thing. With the concrete, I'm not really a concrete guy, so I think these material properties are going to be a little bit more dubious, but I'll just show you the ones that I'm using. Alright. So sorry, let's just clean this up before I go over the material parameters. There we go. Define the concrete material. Okay, so I'm using F prime C. In fact, let us get this to the side here, and I'll show you. So F prime C, I'm using 30 megapascals. That was in the definition. I'm using 10% for the ultimate. So the second one is the ultimate, 10%, pretty standard. Yield strain 0.2%, and this is negative. These values all have to be negative because they're in the compression side. I'm using a ratio of 0.2 for my lambda. I'm not sure about this one. Probably could get a more accurate number. Tension, I'm using 1 megapascal. I think going over 1 mega, I guess it depends on the concrete. Typically lower is better. It's conservative just to assume it's really small. And then for this slope, I'm using a slope that's 20 times less than the original slope for this value. So the original slope is 2 times F prime C divided by the strain. I'm using something that's 20 times that value, 20 times smaller. Those values might totally be 100% unreasonable. At least I think the lambda and the tensile strain ones. If you're a concrete person, feel free to get super mad at me for these properties. But again, I'm not trying to show you the most accurate way of doing it. I'm just trying to get you accustomed with these basic material properties. And we will call the concrete material 3. Hey everyone, so jumping in from the future here, because I lost a little bit of footage, we were about to define the geometry preprocessing. And let's just, to make it really clear why I have this section in here, to define the actual fiber section that we need, we're going to use a patch command. So for the concrete, we'll define everything with one singular patch command, and we'll tell it how many fibers we want. But for the individual rebars, we're going to use the Fibre command. So we're going to need to have the YZ location of each rebar. And we can do this really conveniently by creating an array in Python that just has the information of every rebar. So then when we go to define our fibers, we can just use a loop and it will be really clean. So let's actually, I'll make 2 like kind of subtasks because for the patch command, we need to have the vertices. So we'll go ahead and get that, and we need to be careful because we're going to do it in our local coordinate system. So we're going to get the vertices, and we are going to define rebar information. Info, yeah, that's fine. So if we look at the vertices, let's go, and they make a super big point. They want the corners of the vertices defined counterclockwise. I'm sure a million people have messed this up over the years. I definitely have been this person on multiple occasions. It is a lot harder than you think to keep track of the counterclockwise-ness. But yeah, the reason why this can be difficult, and I'll just pull up a snipping tool here, is when you think of the local axes, it can actually be kind of counterintuitive. So again, if this is the edge here that corresponds to this edge here, we saw that when we defined our element going from 1 to 2, we had a x prime direction like this, x prime. We have a z, or y prime like this, and a z prime being out of the page like this. So this corresponds to a y prime going like this, and a z prime going like this. Note how this is the opposite of the way that you'd normally think it would be. So it would be super easy to define your coordinates and do it in the wrong direction. So just be careful, especially if you're starting out. It can help to draw the diagram out because this is a super easy thing to mess up. So we want the coordinates of our vertices. So we're going to start here, 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 here. So let's just go about defining those right now. So let's create variable. We'll just say h for the height, 600 millimeters, width for width, or w for width. And you know what I'm about to say. These names are totally non-descriptive, but such a small model, it doesn't matter for us. But just so you have in your head, it's really important to be organized. So vertices now, vertices. Can I spell vertices? Okay. So we're going to start bottom left, except for this is in the positive direction. So the first value is going to be negative height divided by 2 and positive width divided by 2. So let's write that out. So it's going to be negative h divided by 2, and then width divided by 2. And let us just copy this a few times. Okay, so for the next point, negative, negative, and we'll go to positive, negative, and positive, positive. Going through that a little quick, but I hope after however many years of education, you can figure it out. Just points on a square. So vertices, what don't you like? Oh, I want to use an NP array. NP, it's generally just better to have NP arrays because you can do a lot of operations to NP arrays that you can't do to regular Python lists. So let's import NumPy. NumPy as NP. Great, we have NumPy. So now we have the vertices. That looks good. Let's clean this up a little bit. All right. Now we can go about defining the information for our rebar. So the first thing we'll do, we'll pull up our Excel sheet and we will copy these in. So we'll create a vector. So rebar z, and then a convenient way of copying this data over is if you copy it and you go Control-Alt-M, this little dialog box pops up. If you paste into that, it will create the NumPy array for you. So a little trick, rebar y equals np.array. Oh, don't need that. Almost played myself. Paste that in. All right, great. And because these are all in millimeters, we will multiply that by our units. Okay, great. And note how we can do this pretty nicely with NumPy. If this was a regular array, you couldn't multiply them all by this value so easily. So now we're going to get the area of the rebar. Okay, so just simple geometry. We know the diameter of the bar because it's a 30mm rebar, and then we just get the area. And now I'm gonna create an array for every single rebar that will contain the YZ information. So I'll just type it out and then we'll go through the code. All right, so let's go through this pretty quickly. I get the number of bars by multiplying the length of my two arrays. This works because we have this convenient grid of bars. If you had something where your rebars weren't in a grid, you'd probably have to manually add one or two entities. We then initialize an array that has a number of rows equal to the number of rebars and two columns. So you can imagine in each row we're going to have the y coordinate and the z coordinate of that rebar. We then assign the values to this rebar by going through these enumerate loops. So we use I and j as our counters. And if you're a cool kid, you use I instead of just I. I guess because I could refer to an imaginary number. Anyways, so we use I, J as our counters, and we use Y as the entry from the variable or the array that we're reading from. So for each Y in our rebar Y array, we pair it with a Z from our rebar Z array. and then we assign it to the appropriate row in our Rebar YZ array. And we can conveniently assign both of the parts of the row at once. So instead of having access, instead of going like 0 equals y and 1 equals z, we can just assign them both at once. So that's what this little thing does. So now we are basically ready to define our sections. Let's just clean this up a little bit. Get rid of some of that white space. And all right, so we will define the test section now. And I will pull up the Wikipedia because I do not have these ones memorized. Section command, fiber section, and copy this guy in. All right, so we don't actually need we don't need the torsional information because we're working in 2D. So that's great, we can get rid of that. And we will use we'll use 1 as the section tag for our test section. Now we need to create the patch command. Let's pull that up. Copy that in. All right. And actually, didn't need an OP right there. All right. So we have our patch material tag. We're going to use 1. 1 was our basic steel section. And that's just the material I'm going to use as our test material. Number of subdivisions in IJ. So that is the number of subdivisions going from the first node to the second node. In our case, IJ is the local Z direction. And then the other one is the local Y direction. So we're going to put one node, and let's add variables. We're going to say n fiber Z equals 1, and n fiber Y is equal to 50. All right. And let's just be super ultra crystal clear about that and what we're doing. So if we look at our section, we define the nodes in the order node I. So this is I, this is J, K, and L. So they're asking for in direction IJ. In that case, that is our Z direction. And we're only defining one fiber because if we think about, like, if we're looking at like moments about the Z axis, it doesn't really help. Like if we add a whole bunch of fibers like this across our section, like all of these fibers are going to have exactly the same Y location. So they're not actually helping us very much. So it's kind of just a waste to have, at least in 2D, to have that extra discretization. So we only want one fiber in the local Z direction, and we're just using 50 in the local Y direction. So hopefully that's crystal clear. And we can assign our vertices using this operation, the star vertices. So what this is basically doing is it's taking every entity of our vertices array and it's unpacking it. So it's taking each of them in order and taking them outside the array. So just a convenient way to add the vertices. So we have the patch. Now let's go about actually assigning the fiber section. And before we do that, let's actually run it. We've made a lot of changes and we haven't really checked if it's going to explode or not. So let's see. Okay, great. We don't have any explosions in our code, so that's good. So we will use a for loop to define to get the coordinates and define our patches. So I'll just type that out now. Okay, so looking at this really quick, we get okay, you know what? A better way. Changed my mind. We'll do it like this. We'll unpack it. Y, Z. There. Less lines of code is always better. So what we do is for each row in our two-dimensional rebar array, we get the YZ, and then we unpack the YZ. So this will give us the Y and the Z when we unpack, because each of these is an array in itself. Each of these is one of the rows. And then we create our fiber and we run it, nothing explodes. We're super happy with ourselves. All right, perfect. So let's clean this up a little bit. I'm going to pull the number of fiber information out because this will apply to both the test section and the real section. Get rid of some of our white space. And then the process is going to be exactly the same for the quote-unquote actual section, but we'll just change the materials. So it will be section 2. The concrete material was 3, so we'll change that. And the steel was 2, so we'll change that. All right, so almost done with defining our sections. We just need to get the transformation and integration. I'll pull up Wikipedia again. So the transformation basically is how the local, if you think of, you have a local beam element, how the forces get changed as it goes from the local to the global system is defined by the transformation. Typically, you're going to just use linear or p delta. Obviously depends on like what you're modeling. We will put both in here. It's a good practice to start with a linear tag and then work your way up in complexity. So even if you're going to use the p delta transformation for real, always start with linear and delta. Okay, perfect. So we have those transformations. Now we need the integrator. So I'll copy this in and then we'll explain what's going on here. So beam integration. Okay, and we're going to assign 1 to our section 1, and we'll put 4 there. Sorry, I will explain this very quickly, or very shortly. So if you recall, when we had our fiber section, there was a number of integration points we defined, or we needed to define across the section. And that's what's going on here. So the integrator command lets us control the integration points in our element, the number that we have, etc. So we're using 4 integration points here with a Lombardo scheme. And if you really want to understand this, you can jump into the theory about that, but I'll skip that for this video. So we'll run, make sure nothing explodes, great. So we are now done defining our sections. Let's just see if anything needs to be cleaned up in terms of spacing. Get rid of some of that white space. All right, pretty happy here. So let's move on and let's start actually defining the sections. This will be pretty simple. So the pre-process is pretty simple. Although, you know what, for posterity's sake, let's actually, let's do this properly. So what I would do whenever I have like some sort of structure, I pretty much have the whole thing defined in Excel. There's pretty much no point. So, well, I'll say this, sections, our section concrete, and I will call this elements, and copy this in, get rid of that. Again, we have such a simple structure. It's like so clear where the X and the Y coordinates are. But I think it's just a good exercise to show you how I would do this if I had a more complicated structure. So I would define the Y coordinates and the X coordinates. Of course, for us, this is like super simple baby stuff. Our X is just 0, and then we're going from 0 to 3 in our Y coordinates. But obviously the structures you're going to be working on are going to be more complicated. So it's just kind of nice to have some sort of visual reference. And that's how I've done it throughout my studies. So, but yes, so let's define our nodes. So I will define coordinates for each node. So node X, this will be an array, and 0, 0, 0. Let's add decimal points so OpenSees doesn't get mad at us for using integers. And then I will copy the Y information in. So that is our X and Y coordinates for the nodes. Now, because we're testing both functions, I will copy these functions below the BuildModel function. And we need, so we have the basic builders and our GetSections. Okay, so that's good. We'll define the nodes in our model using a for loop. And so we'll define the number of nodes. We'll just get the length of one of our vectors. And now for I in range. So we're going to iterate for all of the nodes, and we're going to call a node command. And the first instance is the tag. So because our counter variable is going from 0 to 1 minus this number, we're actually going to add 1 to it. And probably don't have to do this, but just for my sanity, I'm going to call an integer command just to make 100% sure it's an integer. Again, we're only, I've sometimes run into problems where if I'm processing the node tags, somehow they get converted into floats somewhere along the way. So that's why I'm just a little paranoid. So I like to absolutely be sure that it's an integer before I pass it to OpenSees. And then we'll go node X. So we'll access the array of X coordinates. We'll access the array of Y coordinates, and then we should have all the nodes in our model. So let's run that. All right, good, worked. I'll now fix the bottom node. So bottom node is node 1, and we'll fix it in all directions. I'm being a little sloppy with my commenting. So this is where we assign constraints, boundary constraints specifically. And now I think we're good to define our elements. So so my totally inconsistent, for some reason this D doesn't deserve a capital, but this E definitely does. I'm just going to leave it. A regular day in my life. But so we're going to use the force beam column as our elements. So if we look over here, we have our nodes now defined. So we're going to use our elements and beam column elements, force beam column. So in an upcoming video, I'll kind of go into the two important beam columns in detail. But for us today, we're just going to be using it as is. Know that this is a nonlinear beam column element that works with fiber sections. And if you want to know more, I'll get into it more deeply in a future video. So we need to have our element tags. So we'll just say 1, 2, 3. Element nodes. We'll say the first one goes from 1 to 2, 2 to 3, and then 3 to 4. Transfer tag, we're going to use a linear. This is 1. And note something that I don't like so much. It's not super nice to have this as 1 here. It would probably be better to have something a little bit more descriptive. Like if we were to keep track of the linear transfer with a variable that was like lin transfer, and then like assign that to 1. That probably would be a little bit more clean, because when you're going back through and you just see like a 1, you're like, oh god, what on earth does this 1 mean? But I think for now I'm just going to leave this as 1. Our model is like pretty simple, so it's not the end of the world. And we'll use 1 again because that was our test section. Alternatively, that's where it can be really nice to, like I said prior, I used like 10 as the tag for my flexible material. So in my head, I always know if I'm using material 10, it's the flexible one. Similarly, you could kind of assign sections a certain number. So your P delta could always be 2. If you're doing like a test section, maybe your test section is always number 10. And then that way when you see 10, so let's actually do that. And then when we see 10, we know, oh goodness, see, this is where you can mess up. Section was this one. You'll know that it's the correct one. So we don't need any of the mass information. Let's get rid of that. This will bump up to 30. I think anywhere between like 20 and 100 is probably a pretty good number. If you're wondering what this is doing, the force beam column goes through some iterations before the global system goes through iterations. It's pretty complicated, so we're going to kind of skip over that for now. But I think anywhere between 30 and 100 is probably fine. You could go up to 1,000. It's just it will take, the more iterations you do, the longer it takes. And you don't want to be sitting there all day if it's not working. So, and then the tolerance is the tolerance for those sub-iterations. Anywhere between 10 to the negative 6 and 10 to the negative 12 is probably fine. Of course, it depends on your application. And let's actually, that was not so great. I'm going to leave this above commented out, and then we will go and add the OP. So now we're done with defining everything. I want to show you how to quickly visualize your model. We're going to import something else. So recently there was another set of tools that was added to OpenSees in the post-processing. So we're going to import this getRendering function, this getRendering module. And the function from here that we want is called plot models. We'll call this OPP, and then down here we'll go OPP dot get rendering. Oh, no, sorry, plot model. Now when we run this, we'll see an image of the model that we've created. So right here, we can see our simple cantilever, our nodes, our elements, everything looks good. We have a little bit of confidence that this wasn't just a black box, and it kind of makes sense. Something else that we could do to increase our confidence that everything is working our way is we could actually print the variable. Or, you know what, well, even this will be better. I could print the variable, but it's better to return it. So when we run the function now, we'll return the rebar yz variable. And I'm just doing this to confirm that, so you know, when you're going through your models, you can have the confidence that what you're doing actually makes sense. We can see our variable. It's going, we have y starting at negative this 0.225 and going to positive 0.225. This looks like it makes sense. We can see our section. These values match. So that gives us also confidence that we're defining things properly. So that's pretty much it for this video. I think the last thing that we're going to do is I'm going to pop over to that main analysis file and we'll import these functions. So we'll just save that. So we'll go import ModelFunctions as mf, and then we'll just call our functions. So mf dot GetSections. Oh my goodness, GetSections. And mf dot, I think I could remember these things, BuildModel, perfect. So, oh, and we should issue a wipe command and import OpenSees. All right, and we'll import that first. So we'll just check that our main analysis actually runs. Great, so we've imported everything. So we've built our functions to define the model out here in our model functions. Now we're going to import them to our main analysis, and from here we could do whatever we wanted. We could create some analysis functions and analyze our model like that. Really, the sky is our limit. But for this video, I think that's really what I wanted to show. In a future video, I'll show you how to do pushovers using this simple model. So I think that will be exciting. And at some point, I will do a video on the theory behind force-based beam column elements and displacement-based beam column elements. But that one's a little scary because there's a lot of nonlinear stuff going on there. But yeah, so let me know how this all went for you, if it worked out or not. And let me know if there's any videos that you want to see in the future. We're definitely steaming really fast towards pushover videos. And from there, we'll be doing, I think, videos on how to do seismic loads. So that'll be good.